başlayalım. Alright, so let's start with an introduction to lightweight block ciphers. So in order to communicate, we have to first agree on the encoding. Historical ciphers mostly operate on letters since they are pen and paper methods. When working with digital data, we can represent characters as strings of bits. So from strings of bits, we will talk about bytes and so on. Thus, the communicating parties must first agree on an encoding. So generally, we use the ASCII table, but some Turkish characters are not here in this ASCII table. So generally, for Turkish, we use UTF-8 and so on. So some Latin characters are here that we use also in Turkish. But you know, and yumuşak are not here. So this is why we have to use a different table. Okay, but first we assume that we agreed on an encoding. So from this point on, we assume that devices that are going to communicate agreed on an encoding. Okay, so we have the digital data and we agreed on an encoding. Now we are ready to encrypt. So let's first talk about cryptographic goals. So cryptography solves a lot of problems and with different types of cryptographic algorithms. So for the case of confidentiality, we solve this problem with block ciphers and stream ciphers. We also have public key encryption like RSA or AlGamal. So here for the block ciphers, we are going to talk about lightweight block ciphers today, like Heights, Calafia, and Present. We also have authenticated encryption. This actually solves two problems. It both provides encryption, but also authentication. So it solves the problem of confidentiality, but also solves the data authentication. So in this scenario, you also know that the data is authentic and is not changed. Okay. So we will talk about Ascon here, which is already one of the winners of Caesar Cipher, and that algorithm is also a finalist in the ongoing NIST lightweight cryptography competition. So I will show you how an algorithm solves both data authentication and confidentiality problem. So you can also solve the data authentication problem by hash functions or message authentication codes. We also solve the problem of entity authentication, again by message authentication codes, zero knowledge proofs, but generally by digital signatures. Digital signatures also solve the problem of origin non-repudiation. Okay. So there are many topics that needs to be discussed, and there are many lightweight versions of these algorithms. So in this course, we are going to talk about lightweight block ciphers, stream ciphers, authenticated encryption algorithms, hash functions, and so on. Okay. So the NIST doesn't have any standards yet, and they are trying to get a lightweight authenticated encryption standard at the end of this competition, but ISO has many standards for these algorithms. Okay, we will try to cover all of them, but we also will try to cover algorithms in the NIST competition. Okay, that is the main idea. Okay, so some cryptographic algorithms are keyless, like hash functions. They don't need a secret information to run, so you can publicly run it. But other algorithms sometimes require secret key, like symmetric key and asymmetric key cryptography. These two areas also have different names, like secret key cryptography and public key cryptography. So we start with the secret key cryptography. Today we are going to talk about block ciphers. In the secret key algorithms, they use the same key material for both encryption and decryption. So in the block ciphers and stream ciphers, we have a secret key, and we use both of them to have encryption and decryption. This is why we call them the symmetric key cryptography. But in this category, there is also another algorithm. This is not an encryption algorithm. This is message authentication code. So in this scenario, you send your data as a plain text, so you don't encrypt anything. But at the end of your data, you assign a tag like 128 bits, and that tag actually, a person with the secret key can check that your message is not changed during transmission by looking at the tag at the end. Okay. So this is somewhat different than these algorithms. These provide confidentiality. This provides data authentication. That is the main idea. But these algorithms are not completely different than each other because you can use a block cipher to build a stream cipher or a message authentication code or a hash function. So in order to understand all of these topics, we describe them one by one, but at the end you have to come back and try to understand the relation between them. Asymmetric crypto systems have different kind of algorithms. So these different type of algorithms in asymmetric key cryptography include key agreement algorithms like Diffie-Hellman key exchange, public key encryption algorithms like RSA and Algama, and digital signature algorithms like DSA or elliptic curve digital signature algorithm or Schnorr signatures and so on and so forth. So we have many different kinds of algorithms here. So let's first agree on the basic definitions. Plain text is what you want to protect. So a crypto system or a cipher actually consists of two algorithms, encryption and decryption. So your plain text, once encrypted, turns into something unintelligible. So we call it ciphertext. And actually, this should like a random sequence. Looking at this should not give you any information about the plain text. And the person who has the authority to decrypt can obtain the plain text back from the ciphertext. So this is what the cipher means, okay? By cipher, we mean this kind of a crypto system, okay? So in Turkish, cipher is also used for the word password, but they are different things, okay? So in the symmetric key crypto systems, you have the secret key. You use it to encrypt the plain text to obtain the ciphertext. You also use this key material during the decryption. So in order for this communication, you have to give the secret key to the people or the devices you want to communicate in a secure way, okay? So you need a secure channel to do it. So generally, this is done by physically meeting with that person or the device and putting the key there. So think about your SIM cards. Those SIM cards are produced by the GSM authorities. So they put the secret key inside the SIM card, and they also put the same copy to their database. So this way, they give you the SIM card, and they also know the secret key. So both of the devices now have the secret key. This is why you can actually call somebody and talk in an encrypted way. Okay, but this is not always possible. So in the SIM card scenario, because since you are buying a SIM card, so you physically obtain the device. But if you want to do, e-commerce, if you want to buy something from the internet, Amazon cannot go to everybody and give a secret key to them. So you need some different mechanisms here, and Diffie-Hellman key exchange actually works great in this scenario. So it allows you to agree on a secret key in a true and insecure channel. Okay. So let's go back to block ciphers. So block ciphers operate on b-bit blocks of data. This is important because most of the time our plain text can be in a very different types of sizes. So sometimes you might want to encrypt 1 megabyte, but sometimes you want to encrypt the whole hard disk, which might be 1 or 2 terabytes, okay? So designing an algorithm that takes variable input length is a hard process. So for this reason, you actually focus on a fixed amount of bits. So design an algorithm like that. Then you will decide how you are going to, divide your whole data into b-bit blocks. And this actually is related to mode of operations that we are going to talk next week, okay? But let's focus on that our inputs, assume that our input is b-bits. So in practice, this b number is 64 or 128. So generally, we are focusing on 8 bytes or 16 bytes, okay? So plain text is divided into b-bit blocks. Each block is encrypted by a k-bit secret key to produce b-bit output. Output blocks form the ciphertext, but how you form them actually, again, is about mode of operation that we are going to talk about. Some mode of operations are secure, some of them are not. So choosing a block cipher is not enough. So you have to say that which mode of operation you are going to use. So currently our Zoom session is open. So if you look at the settings, it will say that it is using AES 256. This means that AES is the block cipher. 256 is the length of the secret key, but you will see that there's another dash saying GCM. That is the Galois counter mode. So it uses that mode of operation. Without choosing the mode of operation, actually, you cannot use the block cipher. This is why first we need to understand what a block cipher is. Then next week we will talk about mode of operations, okay? So for the rest of this course, just assume that we are encrypting B-bit blocks. Then we will talk about, larger content, okay? Now, if our input is B-bits and the output is B-bits, then what we do is actually as follows. A block cipher and the chosen key is actually a permutation from 2 to the B elements to the 2 to the B elements. Because your input can take 2 to the B different values, starting with B many zeros, going down to B many ones. So there are 2 to the B options. Once you perform encryption on these possible inputs, you use your cipher with a secret key and produce an output. So your input space and output space are the same. So you are mapping this space to itself in different ways, okay? An element goes to a different element. So this is why I call it a permutation. So today, generally, we choose block size as 64 or 128. In some lightweight designs, B can be as small as 32, but choosing something smaller actually makes not much sense, okay? And the secret key, nowadays, we want at least 128-bit security for personal use. But if you want military-grade security, you can increase the key size, okay? Because key size actually determines your security upper bound. Because, for instance, if your secret key is 128 bits, this means that there are 2 to the 128 different possible keys. So you chose only one of them. So an attacker can try one by one, right? So in the worst case scenario, they have to perform 2 to the 128 trials. So this is why it is a security upper bound. But if you design your algorithm in a bad way, then you can break the cipher performing less operations than 2 to the 128. So this is why we want to design something good, but also something fast. So we want to find a sweet spot where it is fast and secure. Okay, that is the whole idea behind this, actually. Modern block ciphers, but also lightweight block ciphers. So let's look at these permutations. So I told you that we are mapping 2 to the B elements to the 2 to the B elements. So question is, how many different permutations can you write in this way? So it is 2 to the B factorial, and it is a very, very huge number. So possible permutations are really huge. But once you choose a secret key and design a block cipher, you're actually, when you design the block cipher for your k-bit key, you are actually choosing 2 to the k permutations from these very, very huge sets. So actually designing a good block cipher means that these permutations are good permutations from this huge space. By good permutation, I'm actually trying to say that it is statistically good. So it doesn't have, non-random behavior. Okay, that is what I'm trying to tell. So as you can see, these are some absolute concepts. It is not easy to measure just by looking these numbers if a cipher is good or not. But this is a big problem in block ciphers, because actually it is not easy to prove that your design is good. So currently, when we design a block cipher, actually designers try to break it with every known cryptanalysis technique. And if it passes all of them, then they announce their cipher. Then crypto community tries to break it, sometimes finding better attacks. But if still the best attacks does not break the cipher, then we start to have confidence in that algorithm. So choosing a standard sometimes takes tens of years, okay? So you cannot just design something and use it that day. That is what I'm trying to tell. For security, for any chosen key, we expect a good block cipher to act like as if it is a randomly selected permutation. Okay. Even more, we expect no relation between permutations that are obtained by keys that are related somehow. So we haven't actually seen details of a block cipher, so these sentences might not mean anything to you right now. But what we are trying to say is that assume that you have chosen a key and a block cipher. So you perform some encryptions and obtain some ciphertext. So if you make a small change in the key, the results should change completely. Okay, this is what we are trying to do. So this is actually related to related key cryptanalysis, which is also sometimes important for lightweight designs, because in the lightweight design, sometimes designers don't focus much on the key schedule algorithm, which allows good related key attacks, which actually happens with heights that I'm going to talk next. Okay. So let's look at design categories. Currently, we can actually categorize block ciphers into 3 groups: Feistel ciphers, substitution permutation networks, and sponge functions or permutation-based functions. So these sponge functions became famous in the last 10 years. And currently, many standards and many new designs are actually based on sponge functions. So it is one of the trending topics in this area. So it is, they deserve attention. Okay. So since we are going to design a cipher, designing something very huge and complex is hard. So main approach is as follows. Let's design something small that is called a round, and then repeat that round many times so that analysis will be easier, but also performance would be good, because it will require less amount of area in the hardware and so on. Okay. So every cipher uses a key schedule algorithm. Most of the time, some lightweight designs don't have a key schedule. So instead of using the secret key directly in every round, a key schedule algorithm is used to generate round keys from the secret key. So you have something called a master secret key, like 128 bits, but then maybe your cipher is 30 rounds, so you generate 30 round keys from this master key. Okay, then use those round keys in the design. So after AES, we talk about this. We had a very nice block cipher, but industry needed some small designs. So instead of asking cryptographers, they designed their own algorithms, and disasters happened. This is why, with a 5 or 10 year delay, cryptographers tried to design lightweight design. So these algorithms designed by cryptographers are most of the time secure and a lot better than the designs by companies. So initial designs by academicians focused on low hardware footprint. So initially they thought that the main problem is the amount of area the algorithm requires on the device, especially on smart cards, because generally you have 1,000 to 2,000 gates that is allowed for you to put a cryptographic algorithm. So they are trying to build something small, like around 2,000 gate equivalents. This is why initial designs focused on the low hardware footprint. Height is one of the IOSS standards, which I broke in my master's thesis. Present Clefia is IOSS lightweight block cipher standard. These two became standard, I think, in 2012. In 2019, they added a third algorithm to this list called LIA. But later on, cryptographers realized that low hardware footprint is not the only problem, because some devices have very limited amount of memory. So they designed algorithms which require low memory consumption. Generally, these are based on small embedded processors. There are some algorithms like I2B, Pride, and SPEC. Some focused on low latency like Prince, and some focused on ease of side channel protection. So sometimes you design an algorithm like Present, but in order for it to be secure against side channel, then you take some precautions. But once you take those precautions, now you're focusing on low hardware footprint becomes meaningless, because due to those precautions, maybe your new design requires thousands of more gates. Okay, so instead of solving the side channel protection after the design, these designs try to provide side channel resistance during the design process. Also, some of them are broken, by the way, in this list. So let's look at Feistel ciphers first. It was introduced by Horst Feistel. A round of a Feistel network consists of a round function and a swap operation. The b-bit input is divided into 2 halves. Round function is applied to one half, and the output is XORed to the other half. Then the places of the halves are swapped. Key material is generally used inside the round function. So here's a picture I tried to draw. So assume that you have a plain text block here. So you divide it into two, saying that this is the right part, this is the left part. So you take the right part, you don't affect anything on the right part, and it becomes the left part in the next round. Okay. But for the left part, right part is fed into a run function. So some operations are performed on it, and the result is XOR to the left part. Okay. So this is the idea. During the run function, we perform operations called confusion and diffusion layers, which provide you the security. But you also use the key material here. Again, instead of using the secret key directly here, generally what we do is to put it into a key schedule algorithm, which provides round keys for every round. Okay. So this is how a Feistel cipher works. I will briefly give an example as this, which is the most famous Feistel cipher, but it is also one of the most known algorithms. After this, then we can move on to lightweight designs and look in detail. This was designed by IBM in the 1970s based on an earlier design by Feistel. So they actually modified their cipher called Lucifer and submitted to this call. In 1976, NSA tweaked the algorithm by changing its S-boxes. So NSA actually made two modifications here. First, they shortened the key because IBM's Lucifer design has a 128-bit key, which was secure. But NSA reduced this key length to 56-bit in DES so that they can perform brute force attacks because they had supercomputers at that time. But they changed the S-boxes so that it becomes more secure. So this way, other countries couldn't break the cipher by techniques like differential cryptanalysis. So block size is 64 bits, key length 56 bits, run number is 16. We generally call this algorithm data encryption algorithm instead of data encryption standard, because if you use the word standard, people still think that it is a standard. They keep using it all the time. I talked to many engineers saying that this is still secure because they say that nobody would bother trying exhaustive search on 56 bits, which actually can be done in a few hours if you have a lot of GPUs or a special device. Okay. For secrecy agencies, they can do it most probably in a few minutes. Okay. So it became useless after 1990s since its short key is susceptible to brute force attacks. But again, people are still using it. Of course, currently we are using a standard based on DES called triple DES. In that scenario, you use the DES algorithm 3 times consecutively, but using 3 different keys. So that is currently secure. And NIST is supporting it until 2024, but they said that they will remove it after 2024. Triple DES is still a IOC standard, and maybe it will stay there for a long time. I don't know. But in Turkey, in credit cards, if you're paying with your contactless payment, I think 40% of them are using AES and 60% of them are using triple DES. Okay, but both of them are currently secure anyway. So this is the picture of DES. So you have the secret key, you perform some permutation on it, rotations, another permutation, and from this 56-bit key, you are producing 48-bit round keys. Okay. So you take the right part of your plain text block, which is 32 bits. You copy half of the bits to obtain 48 bits. This is the expansion function. Then you XOR it with your 48-bit round key. Here you perform S-box operations, then permutation, then XOR with the left part. So 48 bits are shortened here to 32 bits. So this way you XOR it. Now, so you modified the left part, but right part, nothing happened to the right part. So in the next round, it becomes the left part, and the left part becomes the right part. So you keep doing it 16 times, okay? So if you have a picture of this inner part, here we are taking the right 32 bits. It is written like this, 32 bits, all of the lines representing 1 bit. So you clone some of the bits. Okay, so you are expanding 32 bits to 48 bits. XORing with your round key. You have 8 S boxes. These are the S boxes modified by NSA. So they take 6-bit input, but provide 4-bit output. This way, you are actually reducing 48 bits to 32 bits. These 32 bits then shuffled through this permutation operation and then XOR to the left part here. So this is one of the best examples to a block cipher. It uses a Feistel structure. And it was secure for a long time, but currently it is broken due to the short key size. Okay, but we use similar designs. In the lightweight algorithms, we actually perform less operations than this. Okay, so performing less operations than this, but still being secure and faster is a hard problem that's solved by the lightweight cryptography. So we will see some examples like height and Clefia, which are also Feistel ciphers. Then we will also talk about present, which is an SPN cipher.